Hey guys, I'm over in the top right corner now. So basically what we are trying to do is we are trying to understand the relation between two different coordinate systems. The reason why we want to do that is because we are in our journey to express the tensor which is independent of the frame of reference. So in order to do that, we are trying to establish or understand the relation between different frames of reference. And so to understand the relation between two frames of reference, we begin by considering two different coordinate systems. The coordinate systems that we considered in our previous lecture was Cartesian and the spherical coordinate system. Now, since we know the relation, or we were able to arrive at the relation between the Cartesian and the basis of the Cartesian and the spherical coordinate system, using this relation, we were able to prove that the spherical and the Cartesian coordinate systems are inverse of one another. We were able to arrive at the relation between the basis of the spherical and the Cartesian coordinate system, meaning we were able to express x in terms of r and theta, y in terms of r and theta, and similarly r in terms of x and y, and theta in terms of x and y. Using these relation, we were able to prove these coordinate systems are inverse of one another. How we were able to prove that? We took a known quantity and we expressed it a known quantity in a specific coordinate system r that is known in a spherical coordinate system. We expressed it in Cartesian coordinates, and then we replaced the Cartesian coordinates with spherical coordinate, and we were able to recover our r. So we performed an operation to change or express our r in the Cartesian coordinate system, and when we inverse that operation, we were able to recover our r. So it means our spherical and the Cartesian coordinate systems are inverse of one another. Once we established the spherical and the Cartesian coordinate systems are inverse of one another, we took that understanding and then we ascertained the Jacobian of r theta and the Jacobian of x and y. We consider the Jacobian of how the Cartesian coordinates changes with that of the spherical and how the spherical changed with that of the Cartesian. And we took the product of this Jacobian, we ended up having an identity matrix. So what it essentially proves is when my frames of reference or the coordinate systems are inverse of one another, the product of their Jacobian would end up being the identity matrix. Now, with this understanding, we can safely say that when I know the Jacobian matrices of two different coordinate systems, and when I multiply them and I end up with an identity matrix, I can say that these two coordinate systems are inverse of one another. Now, this understanding is what we are going to put to test in this lecture. Meaning, we want to show that these two generic frames of reference are inverse of one another if their product ends up giving us an identity matrix. Now for that, let us consider two frames of reference. One frame of reference that is described by basis I, j and k. Another frame of reference that is described by L, M and N. So I have a frame of reference described by I, j and k and a frame of reference described by L, M and N. Now I can write my I using the frame of reference, my I that is known to me in one frame of reference using another frame of reference or in another frame of reference L, M and M. So I know my basis I in the frame of reference I, j and k, and this basis I am going to represent it using L, M and N. Once I have expressed it, so this is my first numerical operation wherein I am expressing it in terms of L and M, L, M and N. And once I have expressed that, once I have performed this operation, now I'm going to inverse it, meaning I'm going to express my L in terms of I, j and k, M in terms of I, j and k, and N in terms of I, j and k. I'm going to do the inverse of it, wherein I'm going to express my L in terms of I, j and k, M in terms of my I, j and k, N in terms of my I, j and k. So this is essentially the inverse of what I did here. So when I do that, I'm doing the inverse of my operation. So when I'm able to do the inverse of it, then when these two frames of references are inverse of one another, I will be able to recover my I. And the same can be done for J, the same can be done for K. Now this indicates the two frames of references are inverse of one another. But in order to show that I'm able to recover my I, I'm able to recover my j, I'm able to recover my k, I need to know the relation between how I is related to my other coordinate system, how j is related to my other coordinate system, k is related to my other coordinate system, and the vice versa. This proof only works when I know the interrelationship between all the bases of my frames of reference, and often it is not known to us. So this cannot be used as the proof to show that two frames of references are inverse of one another, even though I can use this to define what inverse means. I cannot use this as a proof because this requires that I know the relation between all the bases of my frames of reference. Now, since it is not known to be, we will take up the other approach of finding the Jacobian J1, wherein we are considering how the frame of reference 1, which is I, j and k, changes with respect to the frame of reference 2, which is L, M and N. So the Jacobian 1 talks about how the I, j and k frame of reference changes with respect to L, M and M. Now we are considering another Jacobian wherein we express how the frame of reference L, M and N is changing with reference to I, j and k. So we have two frames of reference. In J1 we are considering how one frame of reference is changing with another. In J2 we are considering how the another frame of reference is changing with the first one. Now we are going to take the product of these two Jacobian, and of course this is going to end up with a square matrix, and the product of these two Jacobian is going to end up with a square matrix here. And now we are going to find out each of these entries. Now the first entry J11 is nothing but the product of this row and the column here. So this is J11. Now what you essentially observe is this expression that relates to that of the J1, that corresponds to J11, can be seen as the chain rule expansion of this relation here. The J11 is nothing but the product of this row to that of this column, which is expressed here. And this summation can be seen as the chain rule expansion of this derivative. So what it essentially means is I'm considering how my I is going to change with respect to my I, but my I is dependent on L, M and N. So what I'm considering is how my I is going to change with respect to my L, and my L is going to change with respect to my I. So that will contribute to my first term. Secondly, I'm going to consider how my I is going to change with respect to my M, and how my M is going to change with respect to my I. That will contribute to my second term and the third term correspondingly. So this is the term, or this is the expression that comes out of the Jacobian multiplication. And this expression here can be viewed as the derivative of I with respect to I, wherein the numerator I is dependent on L, M and N. So when I have this in the first place, I can write this as the chain rule expansion of this. If this is known to me first or a priori, then I can expand this in this form. So ultimately, since now this is known to me, I can rewrite it in this way. Alright, so if this is known to me first, I can expand it using my chain rule in this way. Now this is known to me from Jacobian, I can rewrite it in this manner. So ultimately what I end up having is how my I basis is changing with respect to I. So ultimately this is going to give me 1. Now in the same way, when I consider J12, what I end up having is this expression here, wherein I consider the multiplication of this guy with respect to this guy here. So ultimately what I'm considering is the multiplication of J12 is nothing but the multiplication I'm considering, the multiplication of this row with respect to this column here. I'm multiplying this row to that column here. Now ultimately you end up having these terms here, and when you look closely, these terms can be arrived at when I consider how my I is changing with respect to my J, and then my I is essentially dependent on L, M and N. So I have an I that is dependent on L, M and N. So if this expression is known to me, if this term is known to me first, I have a I that is dependent on L, M and N. I want to know how my I is changing with respect to J. Then using the chain rule, I will be able to write how my I is changing with respect to L and the L is changing with respect to J. That will be my first term. How my I is changing with respect to M and my M is changing with respect to J, second term, and correspondingly I will have my third terms. So if this is known to me, I will be able to arrive at this, but since I have this, I can retrace it back to this. Now it is vital to note that I'm considering how I is changing with respect to my J, and when both these I and J are orthogonal, they are perpendicular to each other, then there is no change in J or no change in I when the J is changing because they are perpendicular to one another. So this term will ultimately become 0. Now this can be extended to J13, wherein I'm considering the product of this row and the final column here, and using the same understanding I can rewrite this summation term as something like this, wherein I'm considering the change in I which is dependent on L, M and N with respect to K. So I can expand, when I know this I can expand it like this, but since this is known I can retrace it back to this. So ultimately I'm considering how I is changing with respect to my K, which is mutually perpendicular. So ultimately this is going to end up with 0. So the key understanding I need to take away, or the key aspect of this derivation, is I'm considering these terms, these summation terms, as the chain rule expansion of a partial set of partial derivatives. So when I take that understanding, I'll be able to rewrite these as this, this and this. And when I'm considering the change in a basis with respect to the same, I end up with 1. When changing the change in basis with respect to any other basis, I end up with 0, assuming that they are mutually perpendicular. So ultimately I'll be able to take the same understanding to J21. This is going to give me this relation, it's going to be 0, J23. So essentially what I'm doing is, or rather J22, multiplying this guy with this guy, I end up with the set of terms here. So when I consider the expansion of the chain rule, I end up with this relation, which is going to give me, which is nothing but how J is changing with respect to J, is going to give me 1. I can do the same for J23, so on and so forth. I will end up with these entities. I'll be able to find out all the individual entries of my matrix, this multiplication matrix. So when I bring all these together, I end up having an identity matrix. So ultimately, the generic matrix that I have considered, or generic frame of reference that I have considered, I, J and K, L and M, they have proved themselves to be inverse of one another. The way I have proved them to be inverse of one another is I have considered their Jacobian and multiplied those Jacobians, and we have shown that, we have seen that these Jacobians ultimately, when we multiply it, give us an identity matrix. So therefore we can say that these frames of reference, these coordinate systems, are inverse of one another. Now the question naturally arises, when can this be non-inverse of one another? When can this be a non-identity matrix? Now the solution to that lies in how we were able to assume that these are 0. By the face of it, it looks as if any random combination of coordinate system is going to be inverse of one another. Because when I take this operation, when I treat the product of their Jacobian as the expansion of the chain rule, in one case I'm going to get 1, in the other case I'm going to get 0. So all the diagonal elements is going to get 1 and all the non-diagonal elements is going to be 0. So it means, it appears as though all the combinations of the frames of reference is going to give me, or going to appear inverse of one another. It's going to hold true. So is that the case? Or can there be any two different frames of reference that are not inverse of one another? This is rather one vital question to answer. Because if this relation is going to hold true for all frames of reference, we can safely say any pair of reference or any pair of coordinate system are inverse of one another. If the product of the Jacobian is always going to be identity matrix, we can safely say that this any two frames of reference, any two coordinate systems are inverse of one another. That can only happen when these terms here, that is the change with respect to I and the of change of I with respect to j is 0, change in I with respect to k is 0, change in j with respect to I is 0, change in j with respect to k is 0, change in k with respect to I is 0. So the product of the Jacobian is going to give me identity matrix only when the change in one basis with respect to another basis of the same coordinate system is 0. Let me repeat. The product of my Jacobian is going to give me identity matrix only when the change in one basis of a coordinate system is independent of change in the another basis of the same coordinate system. So I have a coordinate system I, j and k when the change in I does not influence the change in j, when the change in I does not influence the change in k, and the change in I does not influence the change in L and so on and so forth. When I consider a coordinate system, the change in one basis does not affect the change in another basis. Only then I will be able to show that the product of the Jacobian is identity matrix, and ultimately the two coordinate systems are inverse of one another. Now this is possible only when the basis of my coordinate systems are orthogonal to one another, are perpendicular to one another. If they are not perpendicular to one another, this change will have a non-zero value. 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 Ultimately, I will not have a identity matrix. Ultimately, this will not be equal to an identity matrix when I, j and k are not orthogonal. So the product of the Jacobians then ultimately in that case will be non-diagonal and they will not be non-identity matrix. So in that case the coordinate systems are not inverse of one another. So let's sum it all up. So what essentially we have done is we have considered two generic coordinate systems I, j, k. Let's just for our discussion let's draw it I, j, k, and we have considered another coordinate systems L, m and n. Now we showed that these two coordinate systems are inverse of one another by considering their corresponding Jacobians and taking the product of them. And when we took the product of these two Jacobians, we showed that it ends up with the identity matrix. So ultimately, these two are inverse of one another. Then one question naturally popped up. Is this going to be the case of all pairs of coordinate system? Meaning, if I consider any two random coordinate system, I consider the Jacobian of these two random coordinate system, I take the product of these two Jacobian, is it going to be always identity matrix? If that is the case, then I can safely say that all pairs of coordinate systems are inverse of one another. Is that the case? So we considered that question and we found that only when the basis of an inverse coordinates are orthogonal to one another, you will be able to end up with the identity matrix. If they are not orthogonal to one another, it is one case wherein the coordinate systems are not inverse of one another. You will have a non-diagonal matrix, and that means the coordinate systems are not inverse of one another. So not all pairs of coordinate systems are inverse of one another. Only those pairs with the coordinates perpendicular to one another form a inverse or inverse of one another. So with this understanding, we will wind up this lecture and we will build on this lecture and try to understand or introduce some tensorial notation in the subsequent lecture. Goodbye guys.